Hello all. Today we are dealing with the topic compactness of the integral operator in L2. This is the section 4.5a in the prescribed text of functional analysis. So let's look on to the section. First of all, we are considering a function k of t comma tau belonging to L2 of I square, where I is equal to closed interval 0 comma 1. That is, we are considering a square integrable function k of t comma tau on the space 0 1 cross 0 1, that is our I2. We know what is a norm on L2 of I square, right? So with respect to the definition of that norm, we can say that C is equal to norm of k of t comma tau, which is equal to square root of integral over 0 to 1 integral over 0 to 1 norm of k of t comma tau the whole square dt d2. So using the function k of t comma tau, we define an operator script k on L2 of I. That is, script k is a function from an operator from L2 of I to L2 of I. We are defining this by script k h of t is equal to integral over 0 to 1 k of t comma tau h of tau d2. Okay, we have already seen this operator before, right? And we have proved that this is a bounded and compact operator. Here we are again trying to prove that this operator is compact, but by a different method. In the previous sections, for proving the compactness of this operator, we used the idea that the open ball in L2 of I has an image which is pre-compact. Here, in this section, we are proving the compactness by using the operator with finite rank. Using an operator with finite rank. Okay. In the previous sections, while proving the boundedness of the operator, we have seen that the operator norm of script k is less than or equal to the norm of k of t comma tau. Right. So here we can say that the operator norm of script k is less than or equal to the c. We have defined the c already before. So since L2 of I is a separable complete space, it has a countable orthonormal basis. Okay, let that orthonormal basis on L2 of I be phi I of t, where I varies from I1 to infinity. Okay, then we have a property that phi I of t into phi j of tau, this is phi j of tau, where I comma j varies from 1 to infinity, is an orthonormal basis in L2 of I square. We have used the notation psi ij in the previous section. So we have got an orthonormal basis for L2 of I square. Hence, every element x belongs to L2 of I square has a unique series representation that converges to x itself with respect to the norm in L2 of I square, right? Generally. So, since k of t comma tau is a function in L2 of I square, we can find a unique series representation for k of t comma tau also. Okay, so let that representation be k of t comma tau is equal to summation over I, summation over j, aij phi I of t and phi j into phi j of tau, where aij is a scalar. Okay. The series on the RHS is converging to k of t comma tau itself, that we have already seen. So we are considering the sequence of partial sums of the series representation. Okay. So let kn of t comma tau, which is equal to summation over I equal to 1 to n, summation over j equal to 1 to n, aij phi I of t into phi j of tau, be the sequence of partial sum of the series representation in the RHS of that equation 1. Okay. Now, since the series converges to k of t comma tau, it is obvious that kn of t comma tau, that is the sequence of partial sums, also converges to k of t comma tau, right? So we can say that norm of kn minus k tends to 0 as n tends to infinity with respect to the norm in L2 of I square. Okay. So now we are defining another operator script kn from L2 of I to L2 of I, that is on L2 of I then as script kn into h of t is equal to integral 0 to 1 kn of t comma tau h of tau d2, just like the definition of the script k by that we have defined earlier. Okay. Then we can say that norm of script kn minus script k less than or equal to norm of kn minus k, which tends to 0 as n tends to infinity, right? Where each kn is an operator of finite rank and that rank is less than or equal to n. Okay. So we can just look on to the proof of that the script kn is an operator of finite rank. So we know that script kn into h of t is equal to integral 0 to 1 kn of t comma 2 h of 2 d2, right? And we already got the representation for kn of t comma 2, right? So we are substituting that. So we get integral 0 to 1 summation over I equal to 1 to n summation over j equal to 1 to n aij phi I of t into phi j of tau into h of tau d2. So here the integration is with respect to the variable tau, right? Since this is a finite sum, we can interchange the summation and integration without loss of generality. So we can write the equation as summation over I equal to 1 to n integral over 0 to 1 summation over j equal to 1 to n aij phi j of tau h of tau d2 into phi I of t. Okay, so now for doing the integration we have only the terms with tau, right? Since aij is a scalar and phi j of tau into h of tau d2 is a function in tau, we are integrating this from 0 to 1, right? So we can represent script kn h of t as the summation of product of a scalar and phi I of t, right? That is clear from the equation itself. But we know that phi I of t, where I varies from 1 to infinity, is an orthonormal basis of L2 of I that we have already defined earlier, right? So in the above equation says that we can represent script kn h of t using a finite number of elements from the orthonormal basis. Okay. So the script kn is of finite rank and the rank will be less than or equal to n. This is a proof of what we have already said, that is the script kn is of finite rank. So now since our script kn minus script k tends to 0 as n tends to infinity and each script kn is an operator of finite rank, script k can be approximated by operators of finite rank, right? Or it is the limit of a sequence of operators of finite rank. Also we know that every bounded operator of finite rank is a compact operator that we have already seen in the previous sections. So script kn, we can say that script kn is a compact operator for each small n belongs to the natural numbers. And also we know that the script k is the limit of sequence of operators of finite rank. Right, we have already proved that before. So in short we can say that script k is a limit of sequence of compact operators, right? So hence we can say that the limit operator script k is also compact. How? This is we have already proved this, that the space of all compact operators is a closed subspace of space of all bounded linear operators, that is k of x comma y is a closed subspace of L of x comma y. Okay. So by now we have proved that the script K is also compact by another method that proved we proved this by using an operator of finite rank. So thank you.